there was two guys in the middle when they had the motorcycle like that, and they had helmets on, and they put their helmets together, and then they duct taped their helmets together, and they were in the middle, and their heads were stuck together across the middle, which would be okay, because then they have the R of 0, basically. They're a combined mass. It has an R of 0, the center of the mass, and then but obviously things go wrong and things get off, and they go flying with their heads duct taped together. But I haven't seen that one, and it might be because it violated YouTube's terms of service and stuff. Okay, so let's come down to this. Now we're awake and whatnot. Okay, so now we're talking, so a special case of a normal tangent coordinate system type problem is a case where we have a circular motion, just like we saw there. So something's traveling around a circle, it's a known path. Got somebody's headphones want to connect to my iPad. They're AirPod Maxes. Who's got those things? Those are sick. Somebody just opened the case. No? Okay. They're yours? They're yours. Are they sick? They're pretty cool. I want some. I want to get some. Okay. So a special case would be something traveling in a circle. That's a known path, and so let's talk about how we do a special case, right? In this case, if for a circle, right, it's traveling around with the radius r, right? This thing is going to have two coordinates, right? Our coordinate system, it's tangent to the path and normal to the path. So we're going to have ET and our EN direction would look like this, right? In this particular case, rho, right, is our radius of curvature. Well, it's just going to be constant. It's going to be r. On a typical normal tangent coordinate system, rho could be a function of time too. Rho could be changing as it went along. But when it's traveling around a circle, rho is just going to be that radius r, right? And if I want to calculate change in position, I'll just take r times theta. And that same idea from up above, you're trying to calculate arc length. It's just going to be the radius times the change in angle. And I'll give you the arc length. All right, and so if I talk about velocity then, that's just going to be ds dt. There's going to be d r theta dt, which is going to be r is constant, so that comes out of that derivative there, so it's going to be r theta dot, or it's going to be r times omega in the et direction. So velocity, when something's traveling in a circle, we can define it in terms of omega. It's just going to be r times omega. R times omega is going to be the velocity. And it's always good, that velocity is always going to be in the et direction. Right? And then acceleration, at, is just going to be dv dt, the derivative of r omega, which we just found, dt, again, r is constant, so that comes out. This is just going to be r times omega dot, which is equal to r times alpha in the et direction. Oh, not et direction. That's e. No, that's the at. That's the at. Yep. So that's in the et direction. So that'd be my acceleration in the et direction. Right. But then we have to talk about in the n direction, in the an direction, en direction. My an is equal to, I could write it as v squared over r, or I could write it as r omega squared. Either one. By an. Either one of those forms. Again, if I know velocity, I'll use v squared over r. If I know omega, I'll use r omega squared. Okay? So in a circle, this is what we got. Just got to summarize it. This is just me rewriting what we had above there. The velocity is going to be r in the et direction, and acceleration is going to be either r alpha in the et direction plus v squared over r, or it's going to be r alpha in the et direction plus r omega squared, depending on which one we have. Okay. So one of these problems, and you might have been a little uncomfortable with this, and that's fine, right, is if I was talking about the acceleration and the velocity of this particle right here, if I was talking about acceleration of that particle there, it would have, this is what my acceleration and velocities would be. If my same particle was over here, right, and I was like, what is its acceleration and its velocities over there? it's the same, right? It's independent of where it is on this circle. So this still applies even if the particle's over here. What's different though is where its coordinates are pointed, right? Over here, its coordinates are pointed down here. This is ET hat, and this is EN hat. Okay. So there's no real way to distinguish where it's at on that circle using normal tangent coordinates. And you have to be okay with that. All I know is, I just know that ET is just tangent along the path. I know the path is the circle, even or a circle or whatever path it's on. I know that it's tangent to that path no matter what, and EN is pointed back to the middle, and I know what its magnitude is, but I don't know is, well, if it's that way, or if it's this way, or if it's over here, right? Or if it's up here, right? And I don't really care. Right? Typically, I don't care. I just care, like if I'm trying to calculate, the tension in a rope as it's being whipped around, I don't really care if I'm talking about, is the tension over here, is the tension over here, is the tension there. I just care that there's tension in it, and what is that tension? I don't really care where it's at in the world, okay? Sometimes, though, you do care on where things are at, and that has to do with maybe when, we're gonna do an example a little bit later where say I have another particle over here and it's traveling around a circle, and I want to relate the two, and I want to say, like, are the two going to hit each other at some point, and one's traveling on one path and one's traveling on another path? I need to know where it's at in the world, okay? And so usually in order to do that, you have to get it into some like coordinate system, because this coordinate system, like say if it's traveling on this circle versus a circle over here, the coordinate system of this system over here is not the same as the coordinate system over here. You have to get them in the same coordinate system. And the way you do that is you put them both in Cartesian coordinates. You put them both in Cartesian coordinates, and then you can start making comparisons. So the next little step before we do an example is, how do you get into Cartesian coordinates, okay? And so that's what we're going to do next year. How do you convert between normal tangent and Cartesian coordinates? Because again, normal tangents are just kind of not random, but they're directly associated with the problem that we're dealing with. It's directly associated with that path that you're on. But sometimes you maybe want to make comparisons between two particles on two different things, and you have to get them in the same coordinate system. Okay, so it's a pretty simple just geometry here, right? So say we have this path, right? Here's a path that where to get that? Where the heck did that come from? Oh, right there. So I've got this path, right? It's traveling along this path, and then I put the normal I put a Cartesian coordinate system on it, and I'm going to draw my coordinates here. I got ET is tangent to that path, so my ET hat's going to be doing this. And my EN technically will be perpendicular to that. This angle right here, that would be theta. Right? And what I'm going to do is I'm going to just break this thing up into two different components. There's a component of ET that's going this way, and there's a component of ET that's going this way. So it's just simple geometry, right? When I get in there, I got my ETs doing that, but I could break it up into the I direction and the J direction, just like you would, right? This is just any vector. You could break it up into two different components. Okay, and if you did that, this is what you get. I'll kind of jump to the end here. It's all just based off of that. Similarly, right? You could break this one into two different components as well. That guy and this guy, right? It's pretty simple, a simple idea here. So this is going to be ET hat. This is going to be equal to cosine theta in the I direction plus sine theta in the J direction. Similarly, EN hat is equal to negative sine theta in the I direction plus cosine theta in the J direction. There it is. That's how you do it. So basically, you just determine what your acceleration and velocity are in the ET and the EN direction, and everywhere that you see ET, right, everywhere you see ET, you just put cosine theta in the I plus sine theta in the J, and everywhere that you see EN, you put that. Okay? It's a pretty easy way to convert between the two. And again, you would do this if you really want to know what these coordinates mean in the real world, okay, versus just in that. Okay? Should we do an example? let's do this guy right here. We gotta. Okay. A car travels along a circular path R equals 300 meters. Speed is increased uniformly from 15 meters per second to 27 meters per second in 3 seconds. So it's a constant acceleration going from 15 to 27. And then it takes 3 seconds. And then it's asked for what's the magnitude and acceleration when the velocity equals 20 meters per second. Okay? So it's asking for the acceleration. So let's just write down what the acceleration term is. For this is something that's traveling in a circle. So my acceleration is just going to be AT in the ET direction plus AN in the EN direction. Right? For something traveling in a circle, my AT is just going to be dV dt. Right? And they tell us, so it's just, right, acceleration, with a constant acceleration, if I know change in velocity over to the change in time is all it is. And so they told us that it goes from 15 to 27, right? So this would be 27 minus 15. That's the change in velocity, and it says it takes 3 seconds. And so it's just the constant velocity. So 27 minus 15 divided by 3 would tell me what my acceleration is. My acceleration is in the ET direction, 4 meters per second squared. That's my AT direction. It's just my change in speed, right? The AT is just the change in speed, right? And it's always in the ET direction. But that's not all of my acceleration, right? Because there is that change in direction component that we have to come up with, okay? AN is equal to R omega squared or V squared over R. Either one. Right? In this particular case, it's easier to use V squared over R because I know it asks me what is the acceleration when V is equal to 20. So it tells us that V is equal to 20 in this problem. And so I'm going to use the equation on the right, the V squared over R. So 20 was given to us, squared. The radius in this case is 300. And so my answer ends up being 1.33 meters per second squared. Okay. And so what my that's kind of it. I mean, well, a couple things. There's a couple more things to do. So let's put it in vector notation. So my acceleration vector would be 4 in the ET direction plus 1.33 in the EN direction, meters per second squared. So that is what the vector would look like. All right, and you write it just like that. You put the ET, just say that that's in the ET direction, and then EN is in the EN direction. Do I really care where it's at and which direction it's going? I don't, right? I just want to know what its acceleration is, and that's what its acceleration is. Yes, sir?
Could you show the problem statement again?
Yep. I sure can.
Okay, thanks.
Yeah, and so that's it. I mean, that's almost it. See, this is my acceleration vector. And it takes a little while to get used to, just to be like, well, you know, but you're used to putting maybe I's, J's, and K's here, right, as the thing. Now we're just putting ET and EN, right? And they just signify, right, the ET direction and the EN direction, right? And you keep them separate. You don't ever mix them. Just like you never mix an I and a J and a K when you do stuff, you don't mix an ET and an EN, right? They're two different directions that we're talking about. Okay, but what the problem statement says, what's the magnitude of acceleration? How do I calculate the magnitude of a vector? So yes, square root of the sum of the squares, right? So that's what you would do at this point, right? And oftentimes the magnitude is signified by 2 lines. So if I'm looking for the magnitude of A, that'd be the square root of 4 squared plus 1.33 squared. And so in this case, that ends up being 4.22 meters per second squared. So that's the magnitude of acceleration of that. Right. Okay, so just gonna take a second to point out, terrible handwriting, right? I have terrible handwriting, you all agree? But then look at that solution. That's tight, right? It's really clear what it is that I did. I've highlighted stuff as I go down. As I've had some complaints from your grader saying that not everybody's doing this, okay? So please start doing this. Straight lines, right? It's time to really, right? If you have a tablet, super easy to make straight lines, right? If you don't, it's also super easy to do it. You get a thing called a straight edge, right? Just try not to use it in public too much, right? You'll get beat up. But use just pull out your straight edge and make your drawings with straight edge. It's time, right? Remember, we're gonna let this nerdiness wash over us, and we're gonna become that, and then start using straight edges and making our answers nice, clear, and concise. Right? I think Connor was nice to you this time, and I think he just gave you warnings. But if you're trying to cram, like please go read the section in the syllabus which says how we want the solutions to look like. Nice, clean, tight. Maybe if you're not taking up much room, maybe put 2 problems on one page. Maybe don't cram 50 problems on one page. Right? Try to make it nice and clean and easy to read and stuff. Because again, as engineers, we have to be really clear about our presentation of our solutions. Right? So this is a problem. I'm not going to do this one, but this one has to do with, this would be a case where they give us the position as a function of time, and then you kind of go backwards. So you could calculate what theta dot is, and you could calculate what theta double dot is, which is alpha. And so you kind of go backwards in this case. Instead of starting out with acceleration and going to position, we could start out with position and go to acceleration. These ones are a little bit easier because you're going the other direction. All right, let's look at this guy. All right. This is a little more complicated because we got a couple things going on. We have particle A, right? A car. Is it a car? It's an electric car starting at this position right here. It's accelerating. I give you acceleration as a function of time, and it's going to go whipping around this corner. The whole while, all the way around that corner, it's going to be accelerating at that 1 plus 0.2 meters per second squared. Right? And so it says, tell me what the velocity and acceleration are at point B, right? When I get to point B, obviously the acceleration, there's going to be an acceleration term associated with this at point B, right? But then also there's going to be acceleration back to the middle. There's going to be a centripetal acceleration as it whips around that corner because it's going to have a velocity. There has to be acceleration back this direction. If there's not an acceleration back, if there's no force that direction, no acceleration, you shoot off on a tangent. So we're going to have to calculate. That's where the complexity comes in, is figuring out what the velocity is here so I know it's going back that direction. Or so I can figure out what the acceleration is back that direction. Okay. Let's do this one. All right, velocity isn't so bad there, right? So let's just kind of write down, kind of come up with a plan here, what we're going to do. Velocity is just going to be equal to v in the ET direction. There's going to be ds dt. Oh, dt ds dt. ds dt in the ET direction. Right? So I'll get that, I'll figure that out. I'll figure out what ds dt is in the ET direction. So I'm gonna come up with a velocity equation, and I can come up with that pretty easy. Right? I'll integrate the acceleration and I'll get to that velocity equation, and we'll go from there. Accelerations, again, it's gonna be at in the ET direction plus an in the EN direction. In this case, that's gonna be v dot in the ET direction plus v squared over r in the EN direction. Okay, so this is my answer is going to be at the end. I'm going to have a velocity in the ET direction, and my acceleration is going to have both of these components. Like I was saying earlier, it's going to have this basically acceleration in the ET, a change in speed in the ET direction, plus this centripetal acceleration component. Okay, so let's dive in. Now we know have a plan. So let's figure out what the velocity is going to be at point B over here. Right? I need that, right? I need the velocity at point B because it shows up in that centripetal acceleration term. Right? So now you kind of just treat this as the acceleration a function of time, because it is, right? At is a function of time, which is equal to 1 plus 0.2. 1 plus 0.2 t. That's going to be equal to, right, that's acceleration, that's dv dt. Put all the t's on one side. 1 plus 0.2 t dt is equal to dv. And this is just how you solve acceleration as a function of time, right? We just basically going to integrate. Right? This is going from 0 to t, starting out 0 to t. This is going to go 0 velocity, starting out at rest, to v. Plug that son of a gun into my calculator. And I get t plus 0.1 t squared is equal to v. Integrating dv just would be v minus 0. The other side, right, is just going to be t plus 0.2 t squared over 2, which just becomes that. Right? Or you just do it by hand. I mean, I just did it by, I'm terrible at math, but I can do that integral by myself. Right? So now that's my velocity. This, right? So like we say, you integrate it. I have velocity on one side, and I got t on the other side. So that's velocity as a function of time, right? What you get out of that is velocity as a function of time. Okay? So then this, velocity as a function of time, is equal to ds dt. Right? And so then again, I just put that dt on the other side and integrate one more, and it'll give me s as a function of time. So the integral of t plus 0.1 t squared dt is equal to ds. Integrate this on both sides. This is going from 0 to t, and this is going from 0 to SB. We'll call it SB. And it's going from 0 to whatever the position is out at B. And so if I carried out this, it'd be t squared over 2 plus 0.1 t cubed over 3 is equal to SB. Okay, almost there. We're getting there. So I know I've gotten acceleration, I went to velocity, I got velocity as a function of time, I integrate one more time, and I get position as a function of time. What I'm after now, right now, I need to know how much time it takes me to get to point B. Right? And so I can calculate how far B is. That's actually given to us kind of indirectly, right? We have 200 meters, and then it does a quarter circle over to there, and the radius there is 50. So I can calculate what that distance is to B. So I know what SB is, right? I say SB is equal to 200 plus a quarter circle is going to be pi over 2 times 50. Right? What I'm doing there, right, is I'm just taking, again, the radius multiplied by the angle. Radius times the angle, which is 50. And so that gives me, that's again just arc length. This would be 278.5 meters. So it's got 278.5 meters to get there. And so I can calculate how much time it takes me to get to that point. Right? So I can take this, right, plug it in for that SB right there, and then out of that will come the amount of time. You can solve for t there, plug it in your calculator. T ends up being equal to 16.33 seconds. And again, what I'm at, you're like, where are we headed here? Well, I'm after what the velocity is at the point around the corner, right, at point B. And now I could get it, because now I know how much time it took me to get to that point, right? And then I could just go back up to this velocity equation, right? Now I have a velocity as a function of time. I could then take this and put it back in there, and I could tell you what the velocity is at that position right there, right? And that's it. I mean, once we do that, we're done, mostly, right? So I go back to velocity as a function of time at 16.33 seconds, and out of that, I get 43 meters per second. I might put an arrow here just to show you where that came from. That came from this guy. Okay, what we got? We got 1 minute. Okay, let's finish it up. So then acceleration. They almost have it. So acceleration, I know what velocity is at that point over there, but I need to know what the acceleration is at that point over there too. That's just going to be, I have that, right? AT of t equals 16.33, right? What's given to us was acceleration as a function of time. So I just go back to that original equation, put in 16.33 for time, and I get 4.27 meters per second squared. That's my AT. And then my AN component is just going to be equal to V squared over R. In this case, this is 43 squared divided by 50. 36.98 meters per second squared. And so my total acceleration is going to be 4.27 in the ET direction plus 36.98 in the EN direction. Okay. The first part of the problem said, what is the velocity at t equals 6, or at that point? And there's your velocity. This would be in the ET. One thing maybe short here is that you put an ET there. It'd be in that velocity is in the ET direction, right? But then we also use that velocity in the AN down below too, right? So again, right? What we learned for 1D stuff, we just keep doing it, right? Like this acceleration of function of time, you still need that. We did it for 1D, but this is a 2D problem, but we still use the 1D stuff here, and we work our way through that stuff, and then we get to the two different components, okay? Cool beans? So you have another homework. I think it just goes through it goes through angular motion is the farthest it goes. There's one problem with angular motion, and then it does Cartesian coordinates. And this stuff is going to be on next week. So, cool. Great.